All right, let's dive right into this explainer and look through the director's lens at one of the absolute coolest and, frankly, most challenging parts of computational chemistry. We're talking about simulating molecular dynamics. I want you to imagine you're the director of a blockbuster movie, but instead of A-list Hollywood actors, your stars are proteins, DNA, and chemical compounds. Your job is to capture their exact movements, their reactions, the way they fold. But there's a massive, glaring problem on set. Your biomolecular stars? They literally never act alone. They are constantly surrounded by an environment that dictates their every single move. And that environment is the solvent. Which brings us to the ultimate cinematic question. How on earth do you fit an entire ocean inside a microchip without your hardware completely crashing? It's this incredibly delicate balancing act. You want high-definition physical accuracy, sure, but you also need to keep your rendering times, your computational tractability, from just totally spiraling out of control. To find out how the experts actually pull this off, we're going to run through 5 main acts. We'll set the salvation stage, check out implicit models as our backdrop, explicit models as our extras, run a casting call for water, and finally, look at how we can get the best of both worlds. Okay, Act 1. Let's set the stage. So, in any simulation, your biomolecule is obviously the main character. But solvation is the environment that completely runs the show. It dictates the thermodynamic landscape, which are essentially the invisible forces pushing and pulling your molecule, and its conformational dynamics, meaning how it physically folds and twists in space. Whether a protein folds into this beautiful, stable structure or denatures into a tangled mess, that depends entirely on how it interacts with the solvent around it. Now get this, the sheer scale of this cast is staggering. In a standard simulation, your solvent extras can easily make up over 90% of the atoms in your system. Over 90%. If you have to calculate the forces, the velocities, and the exact coordinates for every single one of those background atoms at every single femtosecond, you are looking at a computationally crushing burden. Act 2. Implicit models, or the backdrop. So how do we handle a scene with way too many extras? Easy. We fake it with a beautiful mathematical backdrop. Think of implicit models as the green screens or the matte paintings of molecular dynamics. Instead of rendering every individual drop of water, this method is super fast and efficient. It replaces millions of individual water molecules with a seamless, continuous medium. By basically integrating out all those discrete molecular details, your computer only has to focus on the star actor. And we have a few common frameworks for this. You've got the Poisson-Boltzmann equation handling the electrical charges, while other mathematical models calculate the physical energy it takes to essentially carve out a cavity in the water. It's a brilliant shortcut that lets us factor in complex quantum mechanics without drowning in data from explicit water atoms. But, and there's always a but, right? While this mathematical green screen is incredibly fast and honestly fantastic if you're exploring vast conformational landscapes, like trying to figure out intrinsically disordered proteins, it definitely has flaws. You lose the physical atom-to-atom interactions. There are no specific hydrogen bonds holding things together. You totally miss out on solvent viscosity, so proteins might move unnaturally fast. Plus, internal salt bridges can get way overstabilized because there's no actual water molecules sneaking in there to disrupt them. If you're designing a highly specific drug, missing those details is a massive deal breaker. Act 3. Explicit models. Let's bring in the extras. What if you, the director, demand absolute realism? You need to animate every single drop of water to capture the true physical chemistry. Well, that's where explicit models come in. This is casting millions of digital extras. You are giving every single water molecule its own exact coordinates, its own Coulomb interactions, and its own Leonard-Jones parameters for dispersion and repulsion. It is highly detailed, deeply realistic, and incredibly computationally expensive. So it boils down to the ultimate trade-off. Do you want the lightning-fast computational speed of the implicit matte backdrop? Or do you absolutely need the high physical fidelity and specific atomic interactions of the explicit extras? Usually, it just depends on what you're trying to observe. But here is where it gets really interesting. You'd naturally assume more detail equals more accuracy, right? Actually, scratch that. Just throwing more extras at a problem doesn't always fix it. Take the Menschutken reaction, a super classic organic chemistry reaction. A 2019 study compared both models for predicting its energy barrier. Shockingly, the out-of-the-box explicit model actually performed the worst. The implicit models were closer to the real experimental data. Why? Because the explicit models were using a fixed set of parameters that completely failed to capture the changing electronic states during the reaction.
explicit models can actually fail drastically if you don't give them proper quantum mechanical end-state corrections.
Act 4. Casting the water. If you decide you do need explicit extras, you can't just grab any random water molecule. You have to cast the right one. We mostly classify these models by how many sites or interaction points they have. Tip 3P uses 3 sites, the oxygen and 2 hydrogens. It's fast, super popular, but tip 4P adds a 4th site, a negative dummy atom, which gives you much better electrostatics, but it costs 1.5 times more computational power. Tip 5P goes even further, adding sites for lone electron pairs. It gives you highly accurate melting times, but boom, it costs 2.5 times more to run. The more accurate the extra, the higher your rendering bill.
And if you cast the wrong extra, it literally ruins your scene. Let's look at TIP3P again. It's highly mobile. In fact, it vastly overestimates how fast water diffuses. So you have these hyperactive water extras bumping into your star protein way too fast and way too hard. In studies of the alpha helical EK peptide, this hyperactive water artificially accelerated the protein's movements, causing it to prematurely unfold and melt. It completely ruined the physical accuracy.
So, enter the A-list extra, the AMOBia model. Most standard models are rigid, their charges are locked in. But real water, it shifts its electronic cloud depending on what's nearby. AMOBia is an explicitly polarizable model. It dynamically adapts its electric field to changing temperatures, pressures, and neighboring molecules. Because it actually responds to its environment in real time and naturally reproduces complex stuff, like water being densest just above freezing, without needing a whole new set of parameters. It's a total game changer.
Act 5. Getting the best of both worlds.
In the modern director's cut, we don't actually have to choose just one method. We combine them into a multi-layered scheme. It perfectly blends those high-definition explicit close-ups with a fast, implicit, wide-shot backdrop. You take a small handful of explicit water molecules and place them in the inner shell, right up against your biomolecule, to handle the critical, specific hydrogen bonds. Then, for the vast outer bulk of the ocean, you use the implicit continuum model. You get local accuracy where it matters and incredible speed everywhere else. I want to leave you with this. Following a paper that reviewed dozens of different water models, an anonymous peer reviewer wrote, 20 years ago, few authors devised a good model of water, gaining fame till the rest of their lives. This manuscript devises 60 very good models of water, and the authors deserve fame as well. Finding the perfect solvent model is this continuously evolving science. Knowing when to cast the explicit extras, when to rely on the implicit backdrop, and how to blend them, that's how we unlock the physical chemistry of the universe. Because when we finally perfect how to simulate a single drop of water, we unlock the ability to design new drugs and understand life at its most fundamental level. So what microscopic movie are you going to direct next?